Hello everyone, in this video we're going to talk about satellite motion and the energy of orbiting objects, and then we'll use that to derive the escape speed velocity. Okay, so the potential energy for gravitation is given by this formula here. Looks very similar to the force due to gravity, but this radius is not squared on the bottom. And so this is used when you have like orbiting objects or when like planetary motion, not normal like on the ground mechanics. So if we had like the Earth here or something, some planet, and maybe we had like a satellite out in space and it's, moving somewhere. It doesn't have to be orbiting, it could also be just moving away. This is where it would have this big G gravitational potential energy. And so when we look at this equation, we see that it's always going to be negative, given by this negative sign, because the masses are going to be positive, the radius is going to be positive, this G is just a constant that's positive. So the gravitational big G potential energy is always going to be negative. And the reason for that is kind of something we can explain using the graph of what this might look like. So when we have a really small radius, this gravitational potential energy is going to be very large in the negative direction, we could say, or very, very negative. So we can start at a very negative. And as the radius gets wider, farther and farther, it's going to get closer and closer to zero. This is the zero axis right here. Okay, so as the radius approaches infinity, or like let's say you had a satellite and it shot out, as it approaches infinity, this potential energy due to the gravity of that planet is going to go to zero. And that's why it's a little different and needs to be given this negative, is because as it gets closer to there, it actually increases the potential energy. Rather than when we thought about potential energy with something on like the ground, if it was on the ground, we usually took our reference to be zero right here. But our reference in this case is like the infinity away from the planet case. And so since we took our reference to be zero, as it got farther away from the ground, it actually had more potential energy. But in this case, as a satellite gets farther and farther from a planet, you can think of it as like less energy of the planet's pulling it in, so there's less potential for it to speed up and get actually closer to that planet. And so that's why we use that convention. Okay, so let's do an example where we derive this escape speed velocity. Okay, so the escape speed velocity, what that means is kind of what this question is saying, is the equation for the minimum speed to launch a rocket to escape the planet's gravitational pull. And so we're going to assume the air resistance is negligible, so there's no external forces, so we can use that conservation of energy. And so we've learned before that the conservation energy is just the initial equals the final. So the kinetic energy plus this gravitational potential energy initial equals the kinetic energy final plus the gravitational final. Okay, so let's think about this now. Let's draw out kind of what we're talking about. So let's say we have a planet and there is some rocket ship that wants to fly away, right? So when it gets launched, it has some velocity initially, and that's what we're going to call the escape speed velocity. That's what we want to find. And we want to find this velocity so that the rocket ship gets so far away that it no longer feels any potential energy from this planet, and we want the lowest speed to do that at. So as we talked about before, as this radius between the planet and the rocket get larger, this potential energy goes to zero. And so if it escapes the planet, it escapes the gravitational pull, the gravitational potential energy is also going to go to zero. So this term is going to go to zero. But now since we want the smallest velocity that does that, we don't want this rocket ship to have any other velocity. Because if it had any other velocity, then we launched it at more than we needed it to, if we want to find this minimum escape speed. And so that means this kinetic energy final also has to go to zero. So it escapes the planet's velocity or gravitational pull just enough to escape it, but not anymore to have any extra kinetic energy. Okay, so let's go ahead and we can just rewrite these variables down here, so we just know that the kinetic energy initial equals, we can subtract it together, it says minus the gravitational initial. Okay, and so now we can plug in what we have here. So we have 1/2, and so the mass here that we're going to use is the kinetic energy, so it's the mass of the rocket or the mass of the object. We'll just say, to generalize, this is the mass of the object. And the velocity is the initial velocity, which is this escape speed velocity, and that's squared. Okay, and then we just had an equation for this, but this whole thing is minus, and this is a minus g. We have the mass of the object, and we also have the mass of the planet that we're on, because we have the two masses over the radius. And so what is this radius going to be? Well, initially, before it's launched, the radius is just the radius of the planet, because it's not above the planet at all. So we can just call this radius of the planet. And so now, these mass of the objects cancel, and these negatives will cancel. So we get 1/2 escape speed velocity squared equals g mass of the planet over radius of the planet. And so now we can just rearrange our variables and get the square root of 2g mass of the planet over radius of the planet. And so that is what we can use as our escape speed. So now if all we need to know is the mass and the radius of the planet, and we can find the minimum speed to launch the rocket to escape the planet's gravitational pull, which is pretty cool. And so we're obviously making some very generalized assumptions, like the air resistance being negligible. There's no like atmosphere pushing on it. But yeah, so that's how you can derive this general equation. Leave your questions down below, and thanks for watching.